Every single time you type a simple prompt into a leading AI model, a silent, incredibly expensive catastrophe occurs behind your screen. To write a word as simple as a massive cluster of hot, energy-hungry microprocessors in a remote data center fires up a trillion distinct connections. It is the computational equivalent of using a cargo ship to deliver a single letter. And right now, this massive brute force approach to artificial intelligence is hitting a hard physical wall. The common belief is that to make artificial intelligence smarter, we just have to make it bigger. For years, the industry followed this exact playbook, stacking layer upon layer of artificial neurons, assuming that a monolithic, all-knowing brain was the only way forward. But that is where everyone was wrong. In our rush to build these giant models, we ignored how biology actually solved the problem of intelligence. Your brain does not fire every single neuron when you read a sentence or tie your shoe. It uses highly localized, incredibly efficient pathways. Our modern deep learning models, however, are forced to use 100% of their capacity for 100% of the tasks we give them. To break free from this computational bottleneck, engineers return to a concept called the Sparse Mixture of Experts. Instead of building one giant, uniform network, they split the system into a collection of specialized subnetworks, which they called experts. A math problem goes to the math expert. A translation task goes to the linguistics expert. To make this work, they placed a digital gatekeeper at the front of the model called a router. Now, when you enter a prompt, the router analyzes the incoming words and instantly switches off 90% of the model, sending the data only to the few experts best suited for the job. On paper, this seemed like the ultimate hack for infinite scale. But the physical reality of training these networks quickly revealed a devastating structural flaw. This is where the simple gating systems broke down. Early routers were incredibly naive. If the router sent slightly more data to one expert at the very beginning of training, that expert naturally got more practice. It became smarter, faster, and more reliable than the others. As a result, the router sent even more data to it, creating a runaway feedback loop. This is known as representation collapse. The favorite expert became completely overwhelmed and burned out, while the remaining experts sat entirely idle, never learning anything at all. To salvage this architecture, researchers had to completely invert how routing works. They abandoned simple gating and moved to what is called expert choice routing. Instead of letting incoming words choose their favorite expert and causing a massive pile-up, the system was redesigned so the experts themselves choose which words to process. Each expert is given a strict capacity limit, functioning like a draft pick in a sports league. This structural twist ensures that every single expert is perfectly utilized, data is distributed evenly, and no computational power is wasted. Yet, this efficiency comes with a silent, massive catch that the industry rarely talks about. While sparse models drastically reduce the mathematical calculations needed to process a token, they create an absolute nightmare for hardware memory. Even though you are only activating 10% of the experts at any given millisecond, the entire model, containing all the silent experts, must still sit active and ready inside the ultra-fast, incredibly expensive memory of your graphics cards. If a model is too large to fit on a single chip, the experts have to be split across multiple physical servers. The bottleneck is no longer how fast the chips can think, but how fast they can talk to each other across cables. This shift in how we build AI changes where these models can actually run. Instead of relying on a massive, centralized cloud infrastructure that requires a constant internet connection and a small power plant to run, sparse expert models open up a different path. By running highly specialized, lightweight subnetworks, we can push advanced intelligence directly to where decisions are made. This means real-time diagnostic systems inside a local hospital clinic, self-correcting industrial machinery on a factory floor, and split-second decision-making inside autonomous systems, all operating locally with minimal power. For the last decade, we lived under the assumption that the path to true artificial intelligence was a straight line of bigger, heavier, more monolithic models. We were wrong. The future of intelligence is not a single, massive, all-knowing mind that must be woken up to do the simplest of tasks. It is a highly coordinated, incredibly fast network of specialists, dynamically turning on and off in the blink of an eye. The era of the monolithic model is over. The era of the dynamic mind has begun.